Okay, greetings. At the risk, more confusion about, and it's only one little question on your exam, but I think it's an important part of if we really understand this, and, and excuse me, how groundbreaking that was to have the action type thing when we're dealing with forces, and so. Because in Aristotle, for thousands of years, I mean, people just thought that objects just wanted to stay put until they were picked up and moved. No, objects want to stay moving or at a constant velocity or at zero, unless there's a net force acting on them, okay, that causes them to accelerate in the same direction as the force, all right? So anyway, other thing about the magnificent Morgan Julo sent me a email saying, hey, this question on the exam, I have no idea what it's, she's going, it's not right. It can't be what it's saying is the right answer. Actually, I shouldn't have said that because it makes Morgan sound like she doesn't know what she's talking. Actually, she does. And it was very subtle and it was a gotcha thing. So I'm going to tell you about it. You go, oh, I got this. I got this. Okay. And I'll probably go ahead and tell you what the freaking answer is to the one that Morgan had a question on, because it was, I didn't realize what I was doing. I got a little bit too enthused, I guess. But anyway, so let's talk about when an object is on the table. Why is the reaction force? Okay, mg is the force of the Earth pulling on the ball, so therefore the pair is the ball pulling, or the book pulling up on the Earth. And then people were going, well, what about the normal force? And I gaffed it off. I didn't answer it because I had an eye, as the wizard would say, you know. Saw my own two eyes. But anyway, it is a little hand wavy, but not much. And we're going to look at the acceleration going around a circle. All right, so I'm going to take my mug off here. I'm dressed very professorial today. Actually, I like wearing tweedy jacket and everything. God, what a cliche. All right, here we go. So, got a book sitting on the table. Okay, here's the table. Here's the book. Now, what I'm going to do is, we got the book sitting on the table, and we already said the Earth is pulling down on the book with a force of mg. So therefore, the book must be pulling up with the same force on this big old Earth, mass of the Earth, times some acceleration upward, which is equal to the mass of the Earth times the acceleration upward is equal to the mass of the book. Let me put it, the magnitudes of those two are equal to each other. Okay? That's the action-reaction forces. But you might be going, well, wait a minute. What about that freaking normal force you've been killing us with for the past 3 weeks? Okay, I'm going to draw a thick table. Here's the tabletop. Tabletop. Okay, so Earth acting on book. Book acting on Earth. Okay, well, here's our book. Let's make this bigger. Here's our big book here. All right. And you know what it's doing? It's smashing down, not because the Earth is causing this to happen to it. It is smashing down on the table. So the book is smashing down on the table right here at this spot. And we just take the center mass of it. Right there is where the book is smashing down on the table with a force of mg. So the table, because the book is smashing down on the table, because the table is smashing down on it, or because the book is smashing down on the table, it is also, that's where we get our normal force. If we had no gravity, there'd be no normal force because everything's floating. In fact, it's a real problem. Because when you're first on a space station or when you're training for that, there is no way you can train for that efficiently, according to all the astronauts that have done that. it takes, several days or even weeks to remember that, hey, I can't just set my pin down here without it floating up in the air and poking me in the eye. I can't do that. If there was all of a sudden zero gravity, I mean, look at this room. I mean, just for giggles, look at this room. Look at my desk. Look at that gut. Anyway, can you imagine if everything, it'd be chaos, more so than it is. All right, so what's the other thing that we wanted to talk about here real quick? The other thing is there's a question on the exam, and I'll probably, and I'll just tell you, it's question 12. I'll tell you right now, because I threw you a curveball. And I didn't mean to, and I don't like to throw you curveballs. I liked the question when I saw it. But it says something like this. It says something like this. It says that we've got a car going around at a constant speed. Okay, we've got a car with a uniform tangential speed of 25 meters per second, say. I don't know what it is. Okay. All right. And then it's going at in uniform circular motion. It's going at a constant speed in a circle. And here's where Morgan got confused. It says the question is, what is the angular acceleration? Here's what Morgan computed. She said, and it said it had a radius of 50 meters, say. It's going around a track, going around a circular track, constant speed in a circle, 25 meters per second with a radius of 50 meters. And Morgan's like, they're showing me that the correct answer is 0 for the angular acceleration. And she's like, that's hooey. I'm not going to say what she actually said. That's hooey because the AC is V squared is 25 squared over 50, which would be 25. Okay, I'm going to do one of my things again. 25 times 25 over 50. That's 25 over 2. That equals 12.5 meters per second squared. Okay? That's not 0. But it's asking for angular acceleration. You don't know about that. Angular acceleration is this. I'm in a and so this is centripetal. Remember, the centripetal acceleration is straight. It's just changing all the time where it's starting from, right? It's always pointing towards the center, wherever the object is. But it's straight. In fact, it's 90 degrees to the velocity, to the linear speed or the tangential speed, or the linear velocity. When we get into rotational things, we'll talk more about this. But the angular acceleration, and that's the problem. I took it from a test bank question that was in the chapter of going around in circles, which we will do after we do energy. Okay, and so here's the deal. The angular acceleration is this little alpha. That's the angular acceleration. And what it means is it's the change in omega over the change in time. In other words, is this speeding up? No. We said it's going at a constant speed around here. So it's going at a constant speed. So what else? What's our other formula for V? V is equal to R times omega. If V is staying the same and R is the same, omega is staying the same. So my change in omega is equal to 0. Okay? In other words, alpha is the angular acceleration, which is in radians per second squared. And we'll talk about that after we talk about work in the next chapter. In fact, we'll get to that not this coming week, but the week after. Okay? So, when you get to chapter 12, if you've watched this video, you've sat through it, you know what the answer is. Is that cheesy or what? Well, I could have just told you at the beginning of the class, but I want you to watch the video. All right? Okay, and I'll let people know, hey, I'm giving you 2 answers on this video. So